Good morning. Today we will talk about ultra high strength steel. In the initial lectures we did mention that strength of metals are several orders of magnitude less than its ideal strength. So, ideal strength we derived is of the order of G by 30, where G is the shear modulus. However, in reality we find that metals deform at a stress much lower than its ideal strength, and this we learned that it is primarily because of the presence of crystal defects like dislocation. If it is possible to produce defect free crystals, we do in fact approach these ideal strength, and which has actually been found in whiskers, which are filamentary crystals which very small dimension, which is virtually dislocation free. But these kinds of material, they are not usable as it is. So, is there a way of improving strength of metal, and particularly today we will see how strength of steel can be increased almost to the order of magnitude of ideal strength of metals. So, under this we will talk about several techniques which have been applied, and we will talk about say few is dual phase steel, we will talk about a special process called patenting, we will talk about osforming, and again many of these cases these using these it is possible to attain very high level of strength even in plain carbon steel. Now, the question then comes up, why do we then go for alloy steel and unnecessarily increase this cost, because most of the alloy additions which are made, they are quite expensive. We will know why do we go for alloy steel. We will talk about two different class of very alloy steels which have very high strength and some very interesting property. Say, we will talk about Maraging steel, we will talk about austenitic stainless steel. Primarily we will talk about its stainless property, and also we will know how our understanding of the principle of physical metallurgy, it has been possible to develop the type of steels, creep resistant steel, which are being used in several high temperature components. Now, let us talk about this dual phase steel. In a dual phase steel, what we do is a normal heat treatment process. We heat, suppose this is the composition of steel, this is the part of the iron carbon diagram, this is austenite, this is ferrite plus cementite region. So, normal structure is something like this. Of this particular composition, you will have parlitic regions and you will have ferrites. These are ferrite grains. So, it is made up of two distinct region. These are the primary ferrite and this is pearlite. Now, when you heat it above this temperature, then what happens? These pearlite, the cementite dissolves in the neighboring cementite, reacts with ferrite and gives you austenite, and this reaction takes place at these interfaces, and gradually the entire this is converted into austenite. So, what you have now here, it will be alpha, that means ferrite plus austenite. So, it is a duplex structure. You can also see the composition. This point will be giving the composition of ferrite, and this point will give you composition of austenite. Now, what will happen? Suppose you quench from here, then what you will have is these ferrite parts they will remain unchanged, but this austenite part will convert into martensite. And then what you will be left with, instead of ferrite pearlite structure, you will get ferrite martensite. And this martensite, since its carbon content is high, it will have very high hardness. So, you have a composite material sort of thing, you have two phased a duplex structure, and so this is the advantage of this intercritical heat treatment, and this can be implemented in mass production as well. And what you see, that depending on the temperature at which this intercritical heat treatment is given, you will have different amount of martensite. You go higher, say if you go beyond this point, this will be 0, almost I mean approaching, says as not 0. So, what will happen beyond this, it will be totally austenite, and if you quench, a part of it will convert into martensite and part will form ferrite. So, if you quench directly from here, because it is a low carbon steel, it has low hardenability, even if you quench it very fast, you may not get completely, if you quench from here, you may not get completely martensitic structure. So, this means say this is the critical point. So, this is A 3. So, this if we say this is A 3. So, if you go above A 3, then there is not much of change. You have a very small amount of martensite and it may have mostly ferrite. This is the percentage phase. Whereas, if your intercritical heat treatment is given here, then you are likely to have somewhere here, then you are likely to have here that amount of austenite, will be proportional to this region, this line, amount of ferrite is this, but this martensite. So, amount of martensite. So, this will be that equilibrium amount, and as you go up, that amount of martensite will change, and also what will happen, this martensite will have a much higher carbon content. So, therefore, its MS temperature is likely to be even possible, it will be MF certainly will be lower than room temperature. So, even if you quench, you are likely to get some amount of retained austenite, and this will goes on decreasing. So, your total structure, say over here, which will consist of ferrite at this, if your this is the intercritical heat treatment temperature, it will be ferrite, martensite plus retained austenite, and as you increase the temperature, amount of retained austenite goes on decreasing, and here of course, you will get ferrite and martensite. But advantage of having a duplex somewhere in between, there is a possibility you will get a martensite, stronger martensite, because we know strength of martensite is a function of carbon content. So, it is likely to have much higher strength, but limitation of this dual phase is the high cooling rate is to be adopted to convert that austenite to martensite in plain carbon steel, and it is applicable to thin plates and sheet. So, the size limitation stays. Now, dual phase steel, what is the most attractive is this gives a better combination of strength and toughness, because many application we know that it is not, strength may not be enough, it must have very high degree of ductility. Look at this, that this is the region which of the dual phase steel, and how does it compare with conventional steel? Conventional steel main strengthening mechanism is solid solution strengthening, and some of the solid solution in phosphorus has a very high degree of little phosphorus can significantly increase the strength, but it segregates, it makes the steel brittle. So, these are the problem. Silicon is a common solid solution strengthener. Manganese of course, does improve, but it is not as strong as phosphorus or silicon. And grain refining is the key strengthening mechanism in case of microalloyed steels. So, where grain refinement we looked at it critically. So, niobium and vanadium. So, carbides and nitrides of these steels, these are the key element, a key constituent which helps or which inhibits austenitic grain growth, and you get a very fine structure. So, compared to all this has better combination of strength and toughness, and it also has good formability. So, that is why there is a special attraction for dual phase steel. Next, let us consider a special heat treatment process called patenting. This is an isothermal heat treatment process. And it gives very high strength steel wire. This is used to produce high strength steel wire. If we look at the time temperature transformation diagram of steel, so this is the A3 temperature, this is A1, and here you have ferrite plus austenite, this side is austenite, and what we tend to do is we cool the steel from above, from the austenitic region. When it is austenite, you cool it almost to the nose here. So, this is the temperature of the surface which will cool slow, this will cool fast, and this is surface, this is the core, and you maintain it in a bath, in a liquid bath consisting of mostly it is lead, and if you have a liquid metal bath, this whole time may help in making the temperature uniform and allow it to cool, allow it transformation to complete to completion at the same temperature, and what we are trying to get is fine pearlite. So, that means lamellar spacing lambda, the lamellar spacing is very small, lamellar spacing is really small, and under optical microscope the pearlite will not resolve. So, normal pearlite you do see these kinds of a lamellar structure, but main idea is if you look at in a standard in an optical microscope, standard optical microscope, and maybe you will find that most of these pearlite nodules are not resolvable. And how it is done? So, these are some through this guide rolls, and this is an ideal guide. So, this is a lead bath, molten lead, and this passes through here. You may straighten this is a roll, and sometime you can heat it also. These you can apply some voltage between this and this, and this is a lead bath, and these are heating coils, and you can also have some this can set up easily in the laboratory. This can set up easily in the laboratory, and you can apply some voltage, and then the wire gets heated up, and this temperature is above A3. It comes into the lead bath, and this is just a guide idle roll, and this wire comes out and it coils here. And by this treatment it is possible to get extremely fine lamellar pearlite, and they have excellent drawing property that they can be cold drawn to desired strength and diameter, and you can get a strength as I has look at this of the order of GPa, gigapascal strength you are getting, and these are used for very high strength applications like spring, then suspension bridges, high tensile wire ropes, and strength will increase definitely as the percentage carbon goes up, and in fact, this lamellar, when you give such high cold working, say maybe say 90% cold work, these lamellar spacings, they become even smaller, and in fact, with the transmission electron microscope people have seen, they come out to be of a nanoscale dimensions, these spacings, as a result of such a large deformations, and that is the responsible for such high level of strength. Now, let us look at another spatial forming process called Oss forming. Now, during microalloyed steel, what we found out is if you work austenite at a lower temperature, that austenite will not recrystallize, and these austenites grains in particular one directions, and if you deform one direction, these grains become highly elongated. So, at least in this one directions they become extremely small dimensions, and they do not recrystallize. So, they will also have high dislocation density. So, rho will be high, dislocation density is high. Now, if you cool austenite to a region, we have seen most steels they have a Benedict bay, and this bay, if you are able to cool at this temperature, and this is the core temperature and this is the surface temperature. When you cool here and then you give working at this region, and here your hold time is sufficiently long, but you make sure you do not go too close to MS. So, in fact, this working has to be done at a temperature higher than MD temperature. This means that if you work, then the martensitic start temperature goes up. The deformation, this is martensitic temperature for certain percentage of deformation. So, do this, give cold working above MD, and after the cold working is over and before this bainite starts forming, you quench the steel, and after this it is necessary to give some tempering, maybe 100 degrees centigrade, you temper to relieve internal stresses. But the key thing is you avoid bainite and you get martensite in cold work austenite. So, austenite is also very hard, within that also you get finer, much finer martensite, and this dislocation density will be much higher, and here you can attain strength level is quite high, yet you will have sufficient ductility, which is not possible in martensite of similar strength. And we will see that although this type of heat treatment can be given in plain carbon steel, often it is not so easy to do so because of section size limitation. But if you go for alloy steel, possibly you can go to a higher in alloy steel, possibly that section size limitation may not be that critical, and we will look at about it. Now, let us look at why do we need alloy addition. So, when we can means why go for such expensive alloy additions when such a wide range of strength and toughness can be achieved in carbon and microalloyed steel. Is it really necessary? Because alloy additions always will make steel expensive. Now, major limitation is in plain carbon steel they have poor hardenability, and you have section size limitation. Say plain carbon steel, say maybe even in a case of infinite quenching, say extremely high rate of quenching, say ideal quenching, you may be able to get through thickness hardness, that means 50% martensite at the core up to let us say maybe depending on carbon content maybe up to say 10 millimeter. So, many application this is too small. Say suppose one application that comes to my mind right now is let us say these landing gears of aircraft. So, this is a part of the aircraft, it has to fly. So, obviously, your aim will be to use very high strength material, so that strength to weight ratio is high. So, it does I mean, so that structure is light, it can fly. And in this case, this dimension of this may be of the order of 80 millimeter dia. So, imagine, so it will be impossible, we know that best property that you can get in steel is through by hardening and tempering, that is tempered martensite gives you the best combination of strength and toughness, and this steel must have high strength as well as toughness. So, it is no way you can achieve this of such a large size. So, here alloy addition becomes a must, and sometime to get certain very specific properties, many applications say nuts and bolts where to make them, they are to be machined. So, this has to be a material should be machinable. So, normal steels the machinability can be improved significantly by not only by heat treatment. Say if you have globular cementite, machinability is higher, but most cases in steel bulk of steels which goes for nuts and bolts may not have a high amount of carbide. So, there machinability is improved by adding some inclusions, particularly in any case to take care of sulfur we add manganese and you form this manganese sulphide inclusions. In fact, for machinable steel intentionally they are sulfurized, sulfur is added intentionally and you add little more of manganese to take care of sulfur, and the presence of this manganese sulphide inclusions gives the steel good machinable property. So, that means not only this hardness limitation, hardenability limitation, but also to give certain very specific properties you need to add some alloy elements. Another important property is corrosion and oxidation resistance. Steel it rust. To protect it from rusting, we use many other techniques as well, like coatings. You galvanize the steel to protect it. For most of the sheet applications, you galvanize steel to protect it for rusting, but many cases this may not work. So, you may need to improve its corrosion resistance. To improve the corrosion resistance, you add certain alloying element, and one of the most common alloy element is chromium. If it is present in dissolved form, it is greater than around 12%, say 12.7 to be specific. See, if it is around 12%, more than 12% chromium, in that case on the steel you have a thin protective coating of oxide which makes steel stainless. So, all stainless steel will have a minimum of 12% chromium, and this chromium must be present in solid solution. Similarly, magnetic properties, to improve magnetic properties, say many applications steel is known for its magnetic property. It is magnetic below the Curie temperature, and one of the main application is, let us say, transformer core. And here when it converts, increases that voltage low to high or high to low, this transformer, the core gets heated, and this is known as hysteresis loss. To cut down the hysteresis loss, often in steel we use some special alloy element, particularly silicon. Some steel you also add phosphorus, electrical grade steels. So, you need to get certain specific properties. Similarly, to get a hard magnetic property, transformer core is a soft magnetic. Similarly, for hard magnetic property, there will be other elements to be special elements to be added. So, that means alloy additions can give are added are necessary to improve certain specific properties. Another major application of steel is in power plants, and power plants, say steam power plants, say boilers, where the steel has to be used at temperature above, say let us say 450 degree centigrade. So, in this case creep becomes and one of the important failure mechanism. So, in this particular case also you need to have some alloy addition which gives it a better corrosion, a better creep resistance. Now, when you add alloy elements to steel, where does it go and what is the role that they play? I think this will vary from element to element. So, here are some common elements which are present in steel. This list is by no means comprehensive, there can be several others also possible, but these are the major alloy elements, and these alloy elements either may be present. So, many of these bulk of the steel which are used is ferritic steel, but bulk of the steel that we use they are ferritic steel, and many of these alloy elements they are soluble to certain, even if it is to a limited extent, they are soluble in ferrite, and in high temperature phase austenite also they have some degree of solubility. So, they will be present as solutes in element in substitutional solute element and ferrite and austenite. Some of the elements that you add, they react with some of the impurities which are present during the steel making stage. There will be oxygen, it reacts with oxygen, form oxide. There will be some sulfur, it reacts with that sulfur and converts into sulphide, and some forms there are silicon is also present in steel, some form silicates. Some examples are given here: manganese sulphide, manganese silicates, iron silicate. So, these are possibilities. You can also have oxides. Aluminum we have seen is used as a deoxidizing agent and it gives fine grain steel. So, alumina is also an inclusions, and some of these inclusions they deform easily during hot rolling, and so these elements, manganese sulphide, if it is present they will get elongated as is silicon, and presence of these elongated inclusions makes the property directional. Say suppose if there is an inclusion like this, so in this transverse direction it will have lower strength. So, it will not affect strength in these directions along the longitudinal directions, but transverse properties, particularly ductility, they get affected. They have they also are difficult to weld because of these inclusions. They give rise to a defect commonly known as lamellar tearing. So, there should be some ways, if these are that inclusion control becomes necessary, shape and size of inclusion control is key to improve its set properties like weldability or transverse strength, whereas these are hard particles, they are present as globules. Some of the elements they may dissolve in cementite like this, and many elements we have seen you add niobium which forms carbide nitrides like vanadium nitride, tungsten also forms carbide, moly also forms carbide, then chromium also forms carbide, and there are certain metals which are added like lead, copper, they are insoluble. So, they are present as globules of lead or copper. Copper is added to some precipitation hardenable grade of steel, HSLA steels, and lead is added to steel to give it good machinability. Now, few of these common alloy elements effect of which are listed here, like chromium, known for its corrosion resistance. We have 12% chrome, steel becomes stainless. Nickel also improves corrosion resistance, particularly in acid sulfuric acid environment. So, many of the stainless steel contains both chromium and nickel, and if you add very high amount of nickel, you can make the austenitic phase stable at room temperature, and we will talk about subsequently. Now, carbides, nitrides and oxides, they act as grain refiner. If you have say tungsten carbide, that will add to abrasion and wear resistance. Some of the carbide like chromium carbides or particularly MOC, molybdenum carbide, they add to some carbides add to creep resistance. These precipitates, if they form along grain boundary, they actually inhibit grain boundary sliding and improves its strength. Similarly, if you have sulphide silicates, they give poor through thickness properties or transverse strength and toughness. It also gives problem with the weldability. These inclusions we just mentioned gives good machinability. Silicon is a low magnetic hysteresis. Addition of manganese, it removes hot shortness. We did talk about it. Problem related to sulfur content in steel. Sulfur segregates to grain boundary, and if manganese is not there, it will form with iron sulphide a low melting eutectic, which makes steel gives a steel its poor hot workability, and this is known as hot shortness. Addition of manganese is extremely important to lower ductile to brittle transition temperature. All cryogenic grade of steel will have sufficiently some amount of manganese. Let us look at a few common ultra high strength steels, and many of these potential applications, obviously they will have so high alloy element, they are expensive, and but nevertheless application like aerospace application where cost may not be a major limitation, because one major criteria is structure should be light and it should be able to fly. So, this is the composition, a very popular grade is EN24 or AISI 4340, by this it is known. These are the composition: 0.4 carbon, 1.8 chromium, 0.8 nickel, 0.25 moly. The moly takes care of many of these steel. When you add these alloy elements, they have a problem of temper brittleness. Addition of moly overcomes that brittleness, and it is used in oil quenched and tempered condition. So, because of these alloy additions, it has a good hardenability. By oil quenching, you will be able to harden through and through of particularly this landing gear type of applications. This is very useful. There is another grade which is almost based on that. Vanadium addition adds to the strength. Here also the treatment is similar: oil quench and temper. Oil quench from that austenitic temperature range, and obviously we will look for fine austenite grain. You do not heat it too high a austenizing temperature. Excuse me. There is a grade called another alloy steel, which has much higher alloy element, and so much of moly present, makes this benetic bay very long. This type of steel, even if you air cool, possibly you will get martensite. So, you can air cool, so your quenching stresses problems are not there, and then you give temper, and it can also be given os forming, and by this you may get even higher strength and toughness properties. Another grade is steel, we will talk about it later separately, Maraging steel. Here this has a very low carbon content, but high nickel, and you have some amount of cobalt, moly, and some to get some precipitation you get titanium and aluminum. Main thing is you look at that carbon content. Martensite is hard because of carbon, and if you reduce carbon to this level, definitely the martensite will be soft. This martensite you can cold work, so they may not have that high hardness, and it is aging, means when you age. So, these are the elements which develop some coherent precipitates in the matrix, and because of the formation of these fine precipitate, its strength goes up. Now, all of these steels, so in this case of course, they have high alloy element. So, they have high hardenability and you can always get strength of these order of GPa order, you have 5% elongations in fairly large section. And as I mentioned here, this is amenable to os forming and you can even get even higher yield strength and ductility. Now, Mahrejing steel, we mentioned that here that martensite is soft, it can be cold work and then it can be given precipitation hardening heat treatment. And typical, and when you give this hardening treatment, aging treatment, the hardness goes up. If you do not give work, if you do not give any cold work, then possibly the hardness increases like this. So, air cooled plus aged. Whereas, if you cold work and then aged, then martensite that in that case in the cold work martensite, when precipitates form, it gives much higher level of strength, and on aging these are the precipitates that form. And they have, because of low carbon content, they have excellent weldability. We will see later that carbon in the main alloy element, which is detrimental, which makes the steel difficult to weld. So, good weldable quality steel, always attempt is made to bring down the carbon content, and here the strength is extremely high. It also have very high fracture toughness. We did talk about K1C, which is a measure of fracture toughness. So, such high level of fracture toughness, 120 MPa root meter square and at 1800 MPa strength is unheard of. So, this is a very special grade of steel. So, here you have strain induced precipitation and which is responsible for its high strength. This is no doubt expensive, you have 18% nickel. Nickel is a very most expensive amongst the common alloy element which are added, and but it is a unique material for rocket casing, aerospace applications. Now, let us talk a bit on stainless steel. Now, we have seen the main alloy element which gives stainless steel is chromium. You must have at least 12% chromium to form protective coating of chromium oxide. Along with that, we also add, to improve corrosion resistance, nickel. It also is an austenite stabilizer. We will see that even add a certain amount of nickel, then the steel becomes austenitic, and we add moly to give it pitting resistance. Now, some of the common austenite stabilizer which are listed here, even carbon is called carbon, nitrogen, they are also good austenite stabilizer. Now, a quick look at this ferritic steel, this chromium iron chromium binary diagram. It is known as a gamma loop forming element. So, here you have ferrite, sometime we call it alpha or delta, does not matter. So, this side is ferritic and here. So, if you amount of chromium goes beyond a critical limit, in that case if you heat the steel iron chromium alloy, it is remains ferritic until it melts. So, you cannot form austenite. So, if you have too much of chromium, then the steel cannot be hardened, given martensitic by quenching. The question of getting martensite does not arise, because you are not able to reach this austenitic state. So, this is one important point you must remember. This is a binary alloy and this composition is quite important, and this gamma loop is around 13%. So, if it is greater than 12.7, then it is ferritic until its melting point. So, this is important to remember. If it is greater than 12.7, then you have no chance of forming austenite.
So, if you have a stainless steel where you have carbon which is we have seen this is a austenite stabilizer. So, if you have some carbon in the steel, effective chromium concentration goes down. So, this is a factor 17 times carbon contained. So, if you have 0.1% carbon means you add to this 1.7. So, 13 plus 2 around 15. So, if this is greater than 15 chromium, in normal steel will always have some amount of carbon. So, if it has around 0.1 carbon, if chromium is greater than 14 or 15, then you do not expect austenite to form, and this type of steel is known as ferritic steel, and it will be stainless because it has more than 12% chromium in solution. And if this is less than this, then we call the steel as a martensitic grade, and common ferritic steels and martensitic steel say compositions are given. One particular composition is 16 chromium, 0.2 carbon. In this case, so 0.12 carbon. You will find it will satisfy this relationship, and this will be ferritic. It cannot be given any hardening treatment. Only way you can harden is some solid solution strengthening or cold working. Whereas, if you have in this particular case 12 chrome 0.15 grade. So, this is a martensitic grade stainless steel. It can be heated to austenitic region, and on quenching you get martensite. So, this is a steel commonly used for cutlery. Some of the turbine blades also and in engine turbine blades are made up of this type of steel. Now, to look at whether the steel what will be the structure of the steel, whether it will be ferritic, whether it will be martensitic, or in the extreme case will it be austenitic. That is represented very well by a diagram called Schaeffler diagram. So, all alloy element can be grouped into two parts. One is a which stabilizes ferrite, another which stabilizes austenite. And what you can find out? You can find out nickel equivalent or chromium equivalent. So, they stand for all ferrite stabilizer. So, factors which are given here. So, some of the elements which are known as very strong ferrite former, they raise the temperature in which ferrite is stable. Look at the vanadium, aluminum, they have very strong ferrite former. Similarly, there are certain other alloy elements like manganese which stabilizes austenite. Carbon is a strong austenite stabilizer, so also nitrogen. So, austenitic grade you try to have high amount of nickel and some of these austenite stabilizer. And it is possible if you have this chromium equivalent around here, chromium equivalent and nickel equivalent here. So, from here onwards, so all these region you will have austenite stable at room temperature, and it is very easy to check whether the stainless steel is austenitic or not, is to check this will be non-magnetic. Gamma is alpha is ferromagnetic, whereas this is non-magnetic, is paramagnetic. So, you will find that this will be attracted by magnet, but not austenitic steel. So, many at times you are one of the main application of austenitic steel is on these utensils. So, when you buy utensils, often you check that whether they are being attracted by magnet. Now, this we have talked about ferritic and martensitic grade of steel. Now, let us look at some austenitic grade of steels. Now, nickel is a very expensive alloy element. So, there have been attempts to have austenitic grade which are cheaper, and there that nickel is substituted either completely or partially, and common elements which are used to substitute primarily is manganese, nitrogen, copper. These are used to stabilize austenite to room temperature, but most common grades, so these are AISI 200 series is manganese substituted stainless austenitic stainless steel. Ferrite and martensitic stainless steel are also stainless, martensitic, but austenitic steel are definitely these are stainless, because it all has very high amount of chromium. One of the popular grade, the most popular grade is AISI 304. Here you have 18 chromium, 8 nickel, but it does, and it has some carbon content, and we will see the effect of carbon a little later, and this is responsible for a problem related to corrosion is called sensitizations. So, under this condition, this does not, these are susceptible to intergranular corrosion, and to avoid that often certain alloying elements are added like moly. It gives a better acid resistance or pitting resistance. You have a little high amount of nickel to give acid resistance. So, this is another popular grade AISI 316. Another is AISI 321. Here you have, this is called stabilized grade. We will see later why stabilized. You add certain amount of very strong carbide former, and another popular grade is AISI 347. This contains niobium, a strong carbide former. This is also a stabilized stainless steel. Now, main important property of austenitic strength steel is it has excellent corrosion and oxidation resistant. It can be used for high temperature applications, and it has not only high strength, good ductility as well, but main problem is it is not amenable to any heat treatment, like martensitic heat treatment is not possible. Only way it can be strengthened is by cold work, and yield strength can be increased to it should be 1000 up to around 1000 by cold work. By giving cold work, you can increase its strength significantly. Now, let us look at what is sensitization. We mentioned that oxidation or corrosion resistance of steel is derived from chromium, and this chromium which must be present when it is present in solid solution, then only the steel has good corrosion resistance. No matter whether it is austenitic or ferritic, this chromium must be present in solid solution. Now, the problem that comes up is austenite can dissolve sufficient amount of carbon as well, and so what happens in this austenitic stainless steel, that carbon which is dissolved in austenite and ferrite which chromium which is also dissolved in austenite, it is possible that they may react to form carbide, and this happens if by chance the steel is heated to these regions, and which is often very common. If you are trying to weld the steel to make a vessel or something, some of the area will be heated to this region, and then this type of precipitation will occur, and when this precipitation occurs, it consumes a significant amount of chromium, around 70% chromium you have in chromium carbide. Then what happens if this chromium carbide forms at the grain boundary, the surrounding region, that chromium gets depleted, all this chromium gets depleted and it comes here. So, you have a region which is depleted of chromium, and this loses stainless or corrosion resistance property. So, therefore, this is where it gets attacked by the environment, and it is susceptible to intergranular cracking, and this is the chromium concentration profile that you can think of. So, this is the base chromium is 12 and suddenly this comes down and near the precipitate is goes up to here it goes up to 70%. Now, the question is, and main reason for this is grain boundary area gets depleted of chromium and lose its stainless characteristics. Therefore, grain boundaries are susceptible to attack and therefore, it is susceptible to intergranular cracking. And how to overcome this? One is, if you quench from above 800 degree centigrade, which is not always possible, then you do not get enough time for this reaction to take place, because above that most of this is soluble in the matrix, which is often not possible. But if a material has been sensitized, if you can give this treatment, then that problem will be overcome. Then other alternative is then reduce carbon. So, there are certain grade like 304, a very low carbon, 304 with a very low carbon. In that case, it is possible that will not be susceptible to this sensitization problem. Another more common way of avoiding it is add strong carbide former like titanium or niobium. Then what happens? This reacts with carbon, this, and then it forms titanium carbide or niobium carbide, and they have stronger affinity for carbon than chromium. So, therefore, chromium does not get enough carbon to react with it, and chromium is forced to remain in solid solution. So, these are the very common way of avoiding that sensitization problem in steel. Now, a quick look at creep resistant steel. Now, we talked about creep, which is a time dependent deformation, any component which is used at a high temperature. In that case, there will be time dependent deformation, and this is a thermally activated process. Now, if you are therefore looking for a steel or any alloy which can withstand high temperature or high stress at high temperature, in that case what do you look for? You look for the material must be able to withstand that environment at that temperature. It must have good oxidation resistance, or it must have good creep resistance. Oxidation resistance, common alloy element is chromium. Creep resistance, common alloy element is moly. Another is structural stability. It should have a very stable structure, and it should have preferably some stable precipitate, and stable precipitates are coherent precipitate. Coherent or semi coherent precipitates are most stable. So, you look for such features in the alloy, and it also often this creep resistant steel, many cases if it is if you are making a boiler superheater, you have to see that not only creep resistance, it must have good weldability, because main fabrication technique will be welding, and these tubes are welded. So, so often there is a limit that it will have lower carbon. Now, the earliest creep resistant steel, older power plants which does not operate at very high temperature, maybe the temperature is around 450 degree centigrade. So, there half moly steel is good for creep resistant, but this is known for a problem called graphitization. Prolonged use at high temperature, carbide gets converted to graphite. So, that is a major problem. So, how to overcome this? This is overcome by adding chromium and add a little bit of moly. So, 2 quaternary 1 moly is a very common creep resistant steel, and this is used at 565 degree centigrade. So, main is a question that comes up, how to improve creep resistance, and it is a time dependent deformation, and deformation we know is the main reason is dislocation glide. If you can make this difficult, how do you make it difficult? You have precipitate, large and many precipitate. You need to have to make this dislocation glide difficult. Sometimes you can make dislocation movement difficult by lowering stacking fault energy, like austenitic steel. They have low stacking fault energy. So, therefore, screw dislocations will be difficult, movement will be cannot cross slip. Then another important factor is a coarse grain, and obviously, when you are looking for creep resistant steel, anything working at a high temperature, you will definitely be looking for steel which has high, or material which has high melting point. And these are the common creep resistant alloys which are listed, we talked about, and this is a newer grade of steel which are currently used in a supercritical power plant. It can go up to 1600 degree centigrade. It has higher amount of chromium and some amount of strong carbide formers, which gives stable carbides, and it forces moly to remain in solid solution to give it better creep resistance. Austenitic steels are good creep resistance, and higher temperature you go for nickel based super alloy. There is often a debate going on whether ferritic steel or austenitic steel are better for creep resistance alloy. So, no doubt at a higher temperature where phase stability is considered, austenitic steel you do not have alternative. This has higher temperature capability, but ferritic steel it is possible to improve its temperature capability to 650 degree centigrade, and because it has certain advantage, like it has low thermal coefficient of expansion, then it has higher thermal conductivity, which are also quite important. So, some of these properties which are comparison is given for ferritic and austenitic steel, and this diagram is actually trying to represent, I will quickly go to that. So, pictorially this is shown as how do you improve the creep resistance. So, you have precipitates, the lambda is the distance between the two, and the key reason is, so this is the creep rate equation, this is dislocation density, Berger vector velocity, and key thing is you can assume that always time to climb is this total time. This time has two component, that these are the layer dislocation pile up which has formed against a particle. Now, dislocation has to climb to overcome this, and this to make this process very difficult. That means, if you make this particle bigger, it will take longer time to climb, and always T climb is much larger than the T glide. So, you can approximate the expression like this. So, what it means, for higher creep resistance you have shorter interparticle spacing and larger particles. So, that is the key. So, with this we stop here, and to sum up, whatever we have covered today is a dual phase steel, a special heat treatment called patenting, another heat treatment called Ostforming. We talked about alloy steel, why it is necessary to add alloy element to steel. We talked about a special grade of steel called Maraging steel and creep resistant steel. Thank you.